Hi everyone, welcome back to Dprieto TV and welcome back to Prietology. We are starting with season 2, and if you haven't watched Prietology, I recommend watching the entire first season, which was about chemistry, up here. So, season 2, our topic, like I said at the beginning, I think at the last episode of season 1, is physics. We will be studying, I think, 6 to 7 episodes of physics, I think. So yeah, this season will be kind of lengthy. So, our first lesson today is called the basics of physics. So today, like we did for the basics of chemistry, we're just laying down the foundation. We're laying down the foundation before we actually get into like doing physics. Okay, so key terms, we have mass, weight, density, speed, acceleration, force, inertia, friction, and gravity. But before we do that, we have to go over something very important that's fundamental to physics. Okay, so like I said, before we begin any physics, we have to go over the system that we'll be using for measurement, the metric system. We will not be using the English system here and whatever. Metric system is used a lot for science, and also in this season we'll be using a lot of math. So metric system has to do with the SI units, so scientific measurement units like moles. I think I talked about that last season. Moles, concentration, molarity, molar mass, a bunch of other stuff, lumens, volts. So we will be using three primary measurements. We'll be using the kilogram, which is for mass and weight, for mass actually, the meter, which is for distance, and second or minute for time. Alright, so our first term is mass. Mass is the amount of matter in an object. So this has mass. This has mass. Our atom model, whose back, has mass. So every single thing except two things do not have mass. Mass is measured in kilos or kilograms. Kilos, kilograms, same thing. It's made with a lowercase k and then a lowercase g. Gravity has no effect on mass. So on Earth, let's say you weigh 200 kilograms, I'm just making this up, 200 kilograms, and if you go to, let's say, Mars, you will still be 200 kilograms in mass. Gravity has no effect. Like I said earlier, everything has matter. The only two things that don't have matter is pure energy and the waves that are carrying that energy, because energy is always carried in waves. Those things do not have mass. And now, one thing I'm starting in Prietology, at the end of every term, I'll just give you a little fun fact about the term. So, a fun fact about mass, the mass of the Earth is 5.976 times 10 to the 24th power kilograms, which is a lot. Alright, so our second term is weight. Weight is a force dependent on gravity. So, unlike mass, your weight actually depends on the gravity of wherever you are. This is scientifically not measured in kilograms. This is measured in a different unit called newtons. Newtons named after Isaac Newton. And then the symbol is represented with a capital N. So if you're gonna say like, oh, my weight is 3 and then a capital N, that's how you would write it. So weight can usually sometimes tell you the force that an object can exert. So like this would probably make a less amount of force than the camera that you're watching me on. It's usually very easy to measure because you just step on a scale and then there's your weight. Weight can also be used to find mass. So like if you say you are 10 times the weight of something, that means you're also 10 times the mass of something. And a fun fact about weight, your weight on the moon is 17% of that of the Earth. So your weight on Mars is 38%, and the weight on Jupiter is 213% of that on Earth. Alright, so our third term is density. Density is how tightly packed a substance or an object is. So basically how tight the atoms are together. So the more tightly packed something is, the more dense it is. And this is measured in, it's a big word, kilos per cubic meter, or lowercase kg / meters and then exponent 3 on top. So buoyancy is basically dependent on density. So things that are less dense will float, and things that are more dense will sink. That's why a piece of paper or like a paper boat would float, and a piece of like a solid piece of steel would like sink to the ground. Dense things usually pack a lot of mass into like one little tiny area, which makes them feel a lot heavier. So a fun fact about density is also a big part in black holes. Since black holes can suck up light, that means the density of a black hole is 1.8 times 10 to the power of 19 kilograms per cubic meter. So like in a meter, that's about that big. It's about 1.8 followed by 19 zeros. That's a lot. Alright, so our fourth term, this is when we actually start getting into motion, is speed. Speed is the distance traveled over time, or speed equals distance over time. That's where our math gets in. So if you travel 50 meters in 10 seconds, that means your speed is 5 meters per second. So this is measured in, like I said, meters per second, so lowercase m / lowercase s. So speed has to do with Newton's first law. So if an object is at rest, or is still going, it'll keep going, or it will stay where it is, unless opposing force blocks it or pushes it somewhere else. Friction is one of the things that can also slow speed down. Fun fact, the speed of light is 300 million meters per second. So in 1 second, light can travel 300 million meters. Alright, so our fifth term is acceleration. Acceleration is any change in speed. So if it goes like, if you're going down a highway and you swerve to the right, that's acceleration. If you're on a highway and then you go faster, that's acceleration. So any change in speed. It is measured in meters per second. So lowercase m / lowercase s squared. So acceleration is not a force. It's a result of unbalanced forces. So say you have, like going back to the highway example, you're going down the highway, then an unbalanced force makes you go forward. So yeah, basically yeah. So when acceleration overcomes inertia, which we will talk about later, you feel a force pushing on you. That is called g-force, or G for gravity. The fun fact, acceleration of a drag racer, a drag racer is 2,400 or 2,400 meters per second. So that's pretty fast. Alright, so our sixth term is force. Force is, like the equation says, force equals the mass times the acceleration. So, like, it partners with mass and acceleration to move things around. So F equals ma is Newton's second law, or if you want it in words, the force required to move an object is equal to its mass times its acceleration. This is measured in newtons, just like, with a capital N. So, like I said, it has to overcome inertia, which we will talk about next, to move. When a force is applied to something and it makes it move, another equal force is applied in the opposite direction, which is Newton's third law. So every action has an equal and opposite reaction. So let me just give you an example. If I push the table here, the table is going to push back with the exact same amount of force, and basically almost nothing happens. Fun fact, there are actually 4 fundamental forces. All the forces in the universe are made out of these 4. The first one is weak nuclear force and strong nuclear force. We'll talk about them later when we get into parts of atoms, more deeper into parts of atoms and radioactivity. And electromagnetism, that's another one we'll get to when we get to electricity. And gravity. Gravity's on this list. Alright, so our seventh term is inertia. Inertia is basically it's a force that makes things hard to stop. So if like a car is just rolling down a highway and there's no way to stop it, it's inertia. So this force is measured in Newton meters. So capital N-M, Newton meters. So like I said, it's an object's resistance to motion as well. So inertia usually works with an object's mass, but momentum works with an object's mass and speed. So something with like a lot of mass that's going at a very high speed has lots of momentum. So, fun fact about inertia, it's used to measure mass in 0 g. I'm not sure how they do that. Alright, so here we have the penultimate term, our 8th term, friction. Friction is a force that tries to stop motion. So like the friction of your shoes tries to stop the motion of your feet so you don't fall. This force is measured in newtons like many other forces. Friction, when friction is applied, it lowers energy, makes heat, and it usually likes to wear things out. Friction also usually works with entropy. We'll talk about entropy next class. And when friction makes heat, the energy is spread out all over the object. So like when you how's a good way, so in a car, when the wheel spins around the axle, after you use the car, there's a lot of friction. So when the axle usually gets very hot, so don't touch it. Friction, fun fact about friction, a drag or the friction on a car is about 280 newtons of force. So 280 newtons of force is trying to stop a car from moving. Alright, so our last term today, gravity. Gravity is a force that occurs between the attraction of two objects. There is really no real measurement for gravity, but there is a measurement for gravitational force, and that is the force in newtons per kilogram. So capital N/lowercase kg. It's one of the 4 fundamental forces like I listed when we were talking about force. It combines with mass and distance to get stronger. So mass and distance would be variable. So if something's more massive, it has more gravitational force. If something is farther or closer, the gravitational force is stronger. The range of gravity, the range of like the pulling range, it's infinite. So like, but farther away, the pole is smaller. So like a star probably like billions of miles away has like microscopically amount of force on our planet. Fun fact, the carrier of gravity, so there's a particle called graviton. It's a carrier of gravity, but we don't know much about it because it's a hypothetical particle. Just some quantum physics for you. Alright, so I think we finished all the key terms for today, so let's move on to experiment of the day. Alright everyone, this is experiment of the day. It's called What Goes Up. So what you need is a large garbage bag. This is just one folded up. 2 plastic sandwich bags, water, some water here, and 2 raw eggs, so like still liquid inside. Okay, so basically we're gonna go outside because this usually gets pretty messy. Alright, so as you see here, we're outside. So Matt is set up on the floor just to catch any broken egg parts that may come out. So what you do, you have 2 bags, get your water, fill 1 bag with it, so that's good. So you fill 1 with water, then you take 1 egg and put it in the water bag. Alright, so we have 1 bag. Then you take another one and just place it in without water. Alright, so now we take this up. Okay, so now we have our eggs. Now we will drop them on 3, 2, 1. Alright. And as we can see, this one is just dead. This one is basically just mush. This one, however, is also kind of mush. But the thing is about this, the shell stayed almost intact. Let's go back inside to examine the results. Okay, so now the experiment is done, we examine the results. So the reason that the egg with the water stayed mostly intact and the other one basically shattered into a million pieces is that when the eggs are dropping, they gain speed. We learned what speed is, so distance over time would be speed. So the more speed they have, the more energy. Without the water protection, the egg without the water breaks and shatters. But the egg with the water spreads out the energy and it doesn't really break that much. So it decreases the speed and also lowers the force of the impact. Looks like that's all for one lesson. So last time, I think last season, we went out of a chemistry book. Now this time we're going out of the same like series but in a physics book. And the experiments are still coming from the big book. I'll leave a link down in the description if you want to find them. Alright, so now that we're done with this lesson, our next lesson is going to be about energy. So potential energy, kinetic energy, and I think we're going to get into black body radiation, I think entropy. So that should be exciting. Well, everyone, thank you for watching, and if you like this video, leave a like and consider subscribing. See ya. Hi everyone, welcome back to Dprieto TV and welcome back to Prietology Season 2. So today is our second episode and today's lesson is called the universals. Like I said last time, we'll be studying energy, black body radiation, entropy, and basically that's what we'll be doing. So let's review our key terms. Alright, so our key terms today we have heat, energy, potential energy, kinetic energy, entropy, vacuum, and black body radiation. So let's get started. Alright, so our first term is heat. Heat is also known as thermal energy, and it is made by rapid atom movement. So I think last season we talked about the states of matter, solid, liquid, gas. Those change depending on heat. So if the substance is solid, then the atom movement is much slower. But if it's a gas, which are usually hotter, those are usually more rapid atom movement. So heat is created by rapid atom movement and it's a form of energy. This scientifically is measured in joules, not Celsius or Fahrenheit. Joules with a capital J, spelled Joules. So hot things usually give off infrared radiation, which I think we will talk about next week, I think. So yeah, hot things give off infrared radiation, causing things to feel hot. Solids, the heat in solids, it's called conduction. And the heat in liquids and gases is called convection. What is conduction and convection, you ask? Conduction is when hot particles, so very hot particles, smash into cooler ones, speeding them up and heating them up. So it's basically like they smash and then so they get hotter and hotter, and then the state of matter changes. And then convection, I think you've heard of this, the heat rises and cold stuff falls. So like hotter things would usually rise to the surface in like water, and colder things would sink. Fun fact, the coldest temperature that I think ever that humans have made on Earth is negative 273.15 degrees Celsius, or in Fahrenheit, negative 459.67 degrees Fahrenheit. Alright, so our second term is energy. Energy is the capacity for doing work. So to do work, you need energy. And this is usually measured in joules and like everything, but it's also measured in calories in food, which is lowercase cal. There are many different forms of energy, like thermal energy that we discussed, which is heat, nuclear energy for power, solar, wind, hydro, there's a bunch of them. Geothermal is one of them. The amount of energy and mass in the universe is constant. Mass in the universe cannot go down because of the laws of thermodynamics, which is matter or energy cannot be created or destroyed, only transformed. So, fun fact about energy, the power output from the sun is 4 times 10 to the 26th power joules per second. So, it's basically a lot of power. Alright, so our third term is potential energy. Potential energy is stored energy that could be made into kinetic energy. So this whiteboard right now is holding potential energy, but then if I move it, it turns into kinetic energy. So this is usually very high tense, like it's very strained and wants to be released. And like energy is measured in joules. This can be in the forms of like catapults, a coiled spring, this right here just staying still, or candy even. Sugar is potential energy. There are 4 forms. One is elastic, so let me get a rubber band out. This can hold potential energy. So if I strain it like that, it's holding elastic potential energy, but if I let go of it like that...
Is that a necklace?
Alright, and another one is gravitational potential energy. So if you hold it like this in the air, it's holding potential energy, but if you release it, it releases the kinetic energy. Chemical potential energy is the chemical... It's kind of hard to explain. So like the chemical bonding before reactions, that's chemical potential energy, and then electrical potential energy, like in batteries. Fun fact, the potential energy in 100 grams of chocolate is 2,000 kilojoules. So 2,000 followed by 3 zeros, that's, let me think, 20 million joules is in 100 grams of chocolate. So basically it has a lot of energy. Alright, so our fourth term is kinetic energy. Kinetic energy is released energy that comes from potential energy, so they are very related. This usually depends on mass and speed, so with mass and speed you can equal kinetic energy. So this is already measured in joules like all other energy. It's the energy for moving things. more speed equals more kinetic energy, so they have a direct relationship. So if you increase the speed, you increase the kinetic energy. This can usually also be made into electricity, so I think when we get to electricity and magnetism, if you spin a magnet around a coil of wire, it can generate some voltage. Entropy is our next term that we'll talk about, can decrease its usefulness. Fun fact, the power of a hurricane, so the kinetic energy of a hurricane, is 1.3 times 10 to the power of 17 joules in one day, if a hurricane lasts a day. Alright, so our fifth term is entropy. Entropy is a measure of disorder or disorganization in the universe. This is usually measured in joules per Kelvin, or J/K. Both are capital. The entropy is the reason that things like a match burns out or a car breaks down. That's because of entropy. Entropy never decreases. The entropy of the universe, the measure of disorder, so the chaos in the universe, will only increase. So the release of potential energy can increase entropy. So when it turns to kinetic energy, that increases entropy, which can lower the amount of kinetic energy, which is basically slowing something down. Fun fact, the lowest boiling point of any element belongs to helium gas. The boiling point of helium is negative 269 degrees Celsius or negative 452 degrees Fahrenheit. Alright, so our sixth term is vacuum. Vacuum is an empty void, usually found in space, devoid of all matter, no matter whatsoever. It has no friction, no pressure, and I think no temperature difference. So its pressure is usually measured in torr. This is the measure of, this is a pressure unit usually used for vacuums. It's torr, lowercase T-O-R-R. Its pressure, again, is measured in torr. So do not step outside. If you're in a vacuum, you need protection. Otherwise, the pressure could explode your lungs, or your blood could boil. So if you step outside in space without a spacesuit, your blood would boil and your lungs would explode. So the pressure in outer space, fun fact, is 10 to the power of negative 16 torr. So basically nothing. Alright, so our last term, our seventh term of the day, is black body radiation. Black body radiation is a dark, mysterious heat monitor of the universe, which means it basically keeps track of all the heat. It absorbs all radiation and re-radiates it as heat. This is why things like asphalt on the ground, so the black stuff on the ground and roads, it gets hot. So this is why black things, if you leave them in the sun, get very hot, because of black body radiation. Absorbs the light and then re-radiates it as heat. Fun fact, the best black body radiation carbon that we've made is 97% of light absorbed that hits it. 97%. That's a huge number compared to other stuff. Well, looks like we finished all the key terms for today, so let's get on to experiment of the day. Alright everyone, this is experiment of the day. It's called Ready, Aim, Fire. What you need, a craft stick, a plastic spoon, 2 rubber bands, a pencil, and some aluminum or tin foil. Alright, so what you need to do, you need to place the stick against the handle of the spoon, so like this. Let's see if I can do it. So like this, and then attach it to the stick with a rubber band. Alright, there we go. It's our spoon is tied. Alright, so now you need to slide the pencil or some stick like this, some cylindrical stick, right here between the spoon and the pencil. So, and then you gotta secure the pencil in place by placing another rubber band around the spoon, the place between the pencil and the stick and the spoon. Alright, should be tight enough. And then now we gotta make a ball out of aluminum foil, so let me just make a quick little ball out of aluminum foil, and then I just crumple it into a little ball, and then I put it in our catapult, and it should launch. Pull it back from here, so we pull back the spoon, and there it goes. It launches. I would say this is a very entertaining experiment. Well, the question is, this is happening because when you push down on the spoon, so when you push down on the spoon here, you transfer potential energy to the spoon and then you hold it in place. When you release the spoon, the energy changes into kinetic, and then the kinetic energy transfers to the ball and launches it across the room. Well, I think that's all for today's lesson. So announcements. I have some sad news to tell you all. So I think that my video about when I returned from a very long unnecessary vacation, I told you that we would do marble racing, but sadly there will be no marble racing this year or ever. I kind of canceled it off my list because we have a lot of videos to get through. So sadly, no marble racing. Alright, so now going on to Prietology. Next episode we will talk about waves. Waves like amplitude, frequency, light waves, gamma, ultraviolet, x-ray. We will talk about waves, only waves that day. So, thank you everyone for watching, and if you like this video, leave a like and consider subscribing. See ya. Hi everyone, welcome back to Dprieto TV and welcome back to Prietology. If you're wondering why I'm dressed like this, it's because I had a formal attending to go to today, so yeah, that's why. Today's episode is episode 3, it's called Doing the Wave. Like I said last time, we'll just be doing waves, so talking about frequency, amplitude, and hopefully the electromagnetic spectrum. So, let's start reviewing our key terms. Alright, so our key terms today is water wave. I'll get into why we're doing water waves. Sound, frequency, amplitude, analog, digital, and the electromagnetic spectrum. So, let's get started. Okay, so our first term is water wave. Water wave, it's kind of like a fundamental idea or thing to get a good type of understanding for a wave. So a wave is a type of energy. So if you think of water waves, they're like this, they flow like that, and so they're a wave. And also water waves are a type of energy. They are kinetic energy. Waves are energy that travel from point A to point B. So one point to another point. So these are usually related to frequency and amplitude. So frequency and amplitude are varying variables between a wave, and waves don't have a specific measurement. They have little different components and parts of it that have specific measurement. So the more energy a wave carries, then it's going to have higher peaks. So water waves are made by moon's gravity. So the moon's gravity pulls on the oceans and then makes the waves. If you're wondering why it doesn't have it on rocks, probably because there's like a stiffer platform because water is more wavy. Fun fact, the height of some killer waves like giant tsunami waves can be up to 15 meters or 49 feet. Alright, so our second term is sound. Sound is a type of energy that can be detected by your eardrum, so they are waves. These are usually measured in decibels with a lowercase d, capital B, so with a small d and a big B. They are longitudinal waves, which means they are waves that are from vibrations and matter. So if I do this, that creates sound, so me hitting this, the energy transfers from it, knocks the matter around the air, and then comes into the camera microphone, and you hear that as sound. These waves cannot travel in vacuum because there's nothing to travel with. There's no matter in vacuum, so you don't hear anything in space. So breaking the sound barrier is going faster than the speed of sound, which is known as a sonic boom. Fun fact, the speed of sound is 300 meters per second, not as fast as light, which is 300,000 kilometers per second. Alright, so our third term is frequency. Frequency is the amount of repeating wave patterns, so the amount of waves in one wave, so the bumps and hills, which are called crests and troughs, so peaks and troughs. Peaks is the high part, troughs is the low part. So the amount of peaks and troughs per unit of time, so hours, minutes, seconds, milliseconds, whatever you want, but it has to be time. This is usually measured in hertz, not this. Ow. Hertz. It's measured in hertz like Hz, which is Hertz, hertz. This is related to pitch and energy of different spectrums. So like pitch, the different frequency can affect pitch, which is how something sounds. Higher frequency means there's more peaks and troughs in a wave. So like I said, it's more compact together, so there's a higher frequency. And usually this means there's a more amount of energy carried in a period of time. So fun fact, the household electricity frequency, because sometimes frequencies can be measured on like those wave graphs like this, they are usually around 50 hertz, so 50 hertz per some unit of time. Alright, so our fourth term is amplitude. Amplitude is a property of all waves, and this is measured in meters. As we know, meters is a lowercase m, and it's a height unit. So the more amplitude a wave has, the more energy carried. What's amplitude, you ask? Amplitude is the height of the crest or peak in a wave. So if you think of a wave like this, the high part, that's the crest. the height between the middle part of the wave. So if a wave moves like this, the middle part of the wave to the highest point is the amplitude. So more amplitude, more energy, and this usually measures a wave's movement. So amplitude is used in AM radios. So the first AM radio transmission, fun fact, was in 1906. So AM radios have been around for more than 400 years. Alright, so our fifth term is analog. Analog is a way to send information using carrier waves. This is usually used in radio and TV broadcasts, so this is more of an old-time technique of sending information. This usually, like I said, transmits information using carrier waves, like radio waves. So radio waves are carrier waves, or electric currents. We'll get into electric currents at the end. That is actually our last episode, electricity and magnetism. So new modulated waves that come from analog waves have the same peaks and troughs as the original. So you send information. It has the same peaks and troughs when it comes back. Fun fact, the first phone call using analog carrier waves was made by Antonio Meucci in 1854. Alright, so our sixth term is digital. Digital is a very sleek and modern thing. It's noise free, so you don't hear that staticky noise. And it's quick and it's easy. Instead of using carrier waves, it uses binary, ones and zeros, which mean either off or on. The 1 meaning on and the 0 meaning off. If you ever look on a lamp, let me see if I can find one really quick. Couldn't find anything. So what I mean by going on and off, if you see on those those lamps that have a little switch and one has like a line and the other has a circle, that's binary. The 1 meaning on and the 0 meaning off. This is usually used in CDs, DVDs, computers, TVs. It basically feeds our modern world. We've gone away from the analog place and we're ready to power our world with digital. So a fun fact is that these were used in the first computer, the Z3, which was made in 1941, probably for World War II. It's getting a little hot in here wearing this thick jacket here. Alright, so our final term is the electromagnetic spectrum. The electromagnetic spectrum is a list of all the waves that we've learned here. So we've learned about water waves, frequency, amplitude. We're taking all this and putting it into the electromagnetic spectrum, which is, like I said, is a list of all the waves in the universe. So the electromagnetic spectrum is a list of waves, like I said, of different frequencies that make up our spectrum of waves. They're all photons, which are little tiny particles the size of electrons. We'll learn about them later. That are different amounts of energy. So the order this goes is the lowest is radio waves, then microwave, infrared, light, ultraviolet, X-rays, and gamma rays. Light is the only visible light band. It's a very tiny band that we can see of radiation. Let me show you a picture of the electromagnetic spectrum. Alright, so here you see a picture from our experiment book. Right there at the end, those are the radio waves, then microwaves, infrared, visible light, ultraviolet, X-rays, and then gamma rays. If you can notice that the radio waves, they're farther apart from each other, each of the crests are farther apart, and in the gamma rays, they're very close to each other. This is something that's called the wavelength, the distance between each crest. So larger wavelength is lower energy. So that's why radio waves, they have the longest wavelength, therefore they have low energy. Gamma rays have low wavelength, therefore they have lots of energy, and gamma rays are very bad for you, so don't mess with them. Well, looks like we covered all our key terms for today, so let's get on to experiment of the day. Alright everyone, this is experiment of the day. It's called lenses and light. What you need, choose 2 sheets of cardstock. These are one of those little folders, like those paper folders. I just cut one side to get some cardstock. A marker, we got one right here. 2 tall clear glasses with straight sides right here. They have a little green at the top, but I don't think that'll affect them. And some water. Alright, so for the procedure, you need to fold the first cardstock in half. So let me fold it in half. Let me put the logo on the inside so it doesn't disturb it. Fold this in half, and then so it can stand up. So now we have to draw an arrow on one of them pointing left. So let me draw one pointing left. There we go. We have our arrow cardstock pointing left. Let's put that over there. Now we need to take the other one and fold it in half as well. And now we have to draw an arrow pointing up. So let me draw an arrow. There we go. We have our arrow pointing up. So now we have to put the empty drinking glass in front of our arrow. Alright, let's do this arrow first. So we have our drinking glass here, if you can see it. We have our drinking glass there, and now we have the empty drinking glass in front of it. And if you look at it, the arrow is a little distorted, but Actually, let me elevate the cup really quick so the arrow is more warped. All right, so there you have the glass. And so now we put it in front of it. It looks like a little distorted sideways arrow. And now we put the thing in front of it, and now we pour water inside this one. Alright, the arrow should be somewhat distorted. Now the arrow, if you see, it's pointing the other way. Let me move the camera this way so you can see it. If you see over here, I don't know if you can see that well, but from here, looks like the arrow is pointing a different way. Let's see if you can see it from over here. There you go, now you can see it better here. It's a little distorted, but you can see the arrow is pointing a different way now. It's pretty cool. Need to clean some things up really quick. The book got wet with water. Alright, so now we're going to take our second arrow pointing up, and then we're going to put the empty glass in front of it. And if we look at our arrow, it looks a little distorted because the glass is not super clear, and it's still pointing up. But now, if we pour the water, let me pour the water off center so the book doesn't get wet again. We have our water here. Now if we put it in front, look at that. Let me see what it looks like here. The arrow almost looks like it's pointing down. It's a little distorted because this is not the clearest glass. Let me move it out a little more. It still kind of looks the same. Looks like the arrow still is pointing up. Interesting. Well, that was kind of a disappointment. I thought the experiment would be better. Well, the reason that the horizontal arrow kind of refracted a bit is because the light bends around the glass. So the glass with the water, it's called a refractor because it refracts the light, which means it bends it a different way. So the glass, like I said, the glass bends the arrow, so the arrow's in a different form. The second arrow doesn't flip, so the arrow, this one, didn't flip because the glass only affects horizontal light. Well, I think that's all for today. So next video for Prietology, our topic is, we're gonna actually revisit an old topic from chemistry, atomic structure. We're going back to that, but we're gonna go even deeper. We only talked about the parts of atoms like protons and neutrons, but now we're gonna see what they're made of. We're gonna see what protons are made of, neutrons are made of, quarks, strong force, and we're even gonna go to antimatter, things that are so expensive to buy they almost feel like they're science fiction. So yeah, it's gonna be a pretty interesting episode next time, so stay tuned. Well, I guess this concludes episode 3, so thank you for watching, and if you like this video, leave a like and consider subscribing. See ya. Happy holidays, everyone, and welcome back to Dprieto TV. Today, we have Prietology, episode 4. It's called The Addams Family. Last time I told you that today we would talk about atomic structure, like we did in season 1, where we talked about atoms, protons, neutrons, and we got a little bit into bonding. Now we're going to see what those protons, neutrons are made of, and other subatomic particles that are in the particle family. So, like I said, today's topic is atomic structure, so let's review our key terms. Alright, so let's review our terms. Today we have atom, electron, proton, neutron, quarks, neutrino, Higgs boson, strong force, and antimatter. 9 terms in total, so let's start with the first one. Alright, so let's start with our first term, atom. An atom is a core of protons, which is represented by a lowercase p with a little superscript plus, and neutrons, which is a lowercase n represented by 0, we'll get to why it's a 0, with electrons, which is represented by a lowercase e with a negative superscript, orbiting it. So everything in the universe is made of atoms, as you guys should know. There are 118 types of atoms because there are 118 elements in the periodic table. which means every element is a specific type of atom, so 118. So, like I said, it's a core of protons and neutrons with electrons. These atoms can lose or gain electrons in chemical reactions. I think we talked about that last season. So, fun fact. The average size of an atom is 1.06 times 10 to the negative 10 meters. So 1.06 followed by 10 zeros, I think. Alright, so our next term is electron. Like I said, electron can be represented also by a lowercase e with a negative sign. So an electron is a fundamental particle, whether you believe it. So it actually has more uses than people think. It is actually, this particle is part of a group called leptons. This is a lepton, and like I said, it orbits the atom core. So this has a negative charge, that's why it has a little negative sign. The number of protons in an atom is equal to the number of electrons, always. These are the particles that are involved in chemical reactions, so these can be given or taken away. Alright, so a fun fact about electrons, the mass of an electron is 9.109 times 10 to the negative 31 kilograms, which is basically like nothing. Alright, so our next term is proton. Proton, like I said, can be represented by a lowercase p with a plus sign. You may think this is a fundamental particle. No, this is not a fundamental particle. This is made of something that scientists like to call quarks. We'll get to quarks a little later after neutron. So neutrons and protons are located in the atom core. They are held together by a force, which is one of the fundamental forces of the universe, along with gravity, strong force. This is a positively charged particle, that's why it has a little plus sign. This, like I said, is made of quarks. It's made of 2 up quarks and 1 down quark. You probably don't know what that means. We'll get to that. Fun fact about protons. The mass is 1.673 times 10 to the negative 27 kilograms. Which is much heavier than a tiny electron. Alright, so our fourth term is neutron. Neutron, like I said, can be represented by a lowercase n with a 0. I'll get to why it's a 0. This, like I said, is a particle in the atom core. This is also not a fundamental particle, but is made of quarks as like our proton. This can only be affected by strong force, which is a thing that holds the atom core together, and gravity. This is a neutrally charged particle, which means it has no charge. That is why it has the 0. No charge. This is made of quarks. This is made of 2 down quarks and 1 up quark. Opposite to what a proton is, which is 2 ups and 1 down. This can usually make radioactive isotopes when you take away some neutrons. The mass of these neutrons is 1.674 times 10 to the negative 27. This is identical, I think, to a proton. Alright, so our fifth term is quarks. This is when it really starts to get interesting. Quarks are basically the building blocks of particles. Protons are made of quarks, neutrons are made of quarks. A bunch of particles out there in the universe are made of quarks. These come in 6 flavors. Flavors means like types. That's what us scientists like to call these. They like to call them flavors. Those 6 flavors are up, down, top, bottom, strange, and charm. You're wondering why they probably call these, right? Like so many weird names like why strange, why charm. Why even call them flavors? I don't know. I'm not a professional scientist. I'm just teaching you guys based on this little textbook, and this little textbook tells me what to teach you, plus I apply some of my own knowledge. Alright, our fun fact is that 2 quarks combined together are a meson, and 3 quarks combined together is a baryon. So protons and neutrons, since they're 3 quarks combined together, they are a baryon, made of 2 ups and 1 down, and one is made of 2 downs and 1 up. Alright, so our 7th term is the Higgs boson. This is a really interesting particle. This is a hypothetical particle, actually. We may not know this actually really exists, but supposedly this particle can give mass to things, so its mass is carrier, the Higgs boson, named after someone Higgs, some person who discovered it in 1950. Like I said, this may not actually exist. We don't know. We may have found evidence of it, but we really don't know. This could be why there's more matter than antimatter in the universe. We'll get to what antimatter is. because these things usually stream around the universe giving mass to things. So it could be. We don't know. It could cluster around particles and then give mass, because you have to remember, this Higgs boson is the carrier of mass. This gives mass to things in the universe. Fun fact, the energy of the beam that made it, and I think it was made in the Hadron Collider in Switzerland, the beam that made it was 350 megajoules. 350 million joules of energy. What? Alright, so our second to last term is strong force. Strong force is one of the 4 fundamental forces of the universe, and this is the strongest force, obviously. This is the force that can hold the nucleus of the atom together, because electromagnetism, another fundamental force, wants to repel them away. But strong force has to be very, very powerful to keep them all together, which takes a lot of force. So this can usually make radioactivity and alpha particles. We will get into that next class. Its range is only 10 to the negative power of negative 15 meters. So it's a very small range, unlike gravity, which has an infinite range. Fun fact, its carrier, or the particle that carries it throughout the universe, is called gluon. Gluon sounds like glue. That's what you can remember. Gluon is a character of strong force, because gluon can help hold things together. So yeah, its carrier is gluon, and it helps hold the stuff. It helps hold the nucleus together. All right, so our last term is antimatter. Antimatter is like the evil twin of matter. Like literally, this is the evil twin. It's the entire opposite of matter. All its properties of matter is reversed, except mass. It still has the same mass as matter. But if you combine antimatter and matter together, it'll create an explosion in the universe so big it releases a flash of raw energy across the universe. This mass of antimatter is instantly transformed into highly energized gamma rays. We learned about gamma rays last time. They're super high energy waves that can give you cancer and mess up your cells. So this is gamma ray, but really high energy. Fun fact, the cost of a milligram of antimatter is $300 billion for a milligram. 1,000th of a gram costs $300 billion. You can imagine how much a kilogram would cost if this is like that. Actually, let's do the math. Okay, I got it. It's 300 million billions of dollars in 1 kilogram of antimatter. So that gives you the ridiculous cost, but this also could be a futuristic energy source according to scientists. Well, looks like we finished all our key terms for today, so yeah, there's no experiment for today. So let's just get on to announcements. Alright, so announcements. Sadly, we don't have an experiment for today. Alright, announcement number 1, a Christmas special. Coming soon this month. We couldn't do a Thanksgiving special because of all this COVID crisis, family, traveling thing stuff. There may also, this year, I'm planning on maybe doing a live stream on New Year's. So if I do one, come and join the fun. Alright, in January, second announcement, January of 2021, there will be a new game coming. It's called Cuphead, right here. I'm going to try playing Cuphead. I'm going to be horrible at it. Well, that's all. Oh, also, one more thing, going back to particles. These particles, like we all talked about, so quarks, neutrinos, protons, neutrons, Higgs boson, they can all be organized onto one chart. It's called the Standard Model. Can you put another picture up here? Yeah. This is the Standard Model right here. So yeah, I just wanted to put that out before we conclude today's episode. Next episode, we will be talking about radioactivity. So alpha particles, beta particles, radioactivity, radiation, Schrodinger's cat, the cat in the box experiment. We'll get into that. Well, I guess this concludes episode 4. So thank you for watching. If you like this video, subscribe and leave a like. Anyway. See ya. Hi everyone, welcome back to Dprieto TV and Happy New Year! We go into Prietology again. This is episode 5 of season 2. Today's topic, like I said last class, is radioactivity. We have 6 key terms today, so other than that, let's get started. Alright, so let's review our key terms that we have. So we have 6 terms for today. We have radioactivity, alpha particle, beta particle, photon, Schrödinger, what a fun word to say, Schrödinger's cat, and weak force, one of the fundamental forces of the universe. So let's start with our first term. Alright, so let's start with our first term, radioactivity. Radioactivity is the action that happens when atoms break down, so basically when they collapse on themselves. Radioactivity can affect atoms with more than 83 electrons because remember, I think we talked about this in season 1, the number of protons of the element is also the atomic number of the element. So elements number 82, so uranium and below, so uranium to hydrogen, those are all naturally stable except for a little few radioactive ones, one in there. But 83 and above, those are all radioactive and are subject to radioactivity. Radioactivity is usually a battle between electromagnetism, which we'll talk about next class, and strong force. Both are fundamental forces in the universe. This makes a nucleus split apart and emit alpha particles, beta particles, and destructive gamma rays. We learned about gamma rays when we talked about waves 2 classes ago. They're very, very high energy and can cause cancer and split DNA. So fun fact, radioactivity was actually discovered in 1896. So the discovery of radioactivity has actually been around for a pretty long time. Alright, so we are on to our second term, alpha particles, or alpha particle. Like I said last time, this is one of the results of radioactivity. This is the largest particle in nuclear radiation, and this can be stopped by something as thin as a sheet of paper. So a little piece of paper can stop an alpha particle. This can be slow moving and very destructive. It's not as fast moving as beta particle. It's very slow moving and, like I said, can be destructive. This is also known as a very heavy helium nucleus. So imagine a nucleus, a helium atom. It's just a nucleus. That's an alpha particle. Just a nucleus of a helium atom. So the fun fact about alpha particles is its weight is 6.644656 times 10 to the negative 27 kilograms. That, on a scientific scale, is pretty big. Alright, so our third term we're almost halfway through, is beta particle. Beta particle is basically almost the opposite of an alpha particle. This is a very fast moving particle, unlike its partner alpha particle, which is a very slow moving one. This is actually an electron, a very speedy, highly charged electron. It's negative charge without a nucleus, so it's basically just a random it's basically just as scientists say, free electron that's whizzing around in the air without a nucleus attached to it. This is 7,000 times lighter than the alpha particle, which is a huge scale, and this can be stopped by something as thin as a little sheet of metal. So a thin sheet of metal is able to stop a beta particle, but that's a lot more compared to a thin sheet of paper. Fun fact, the mass of this is 9.109 times 10 to the negative 31 kilograms. You might think, hey, 9 for the beta particle is greater than 6 for the alpha particle. Why this is lighter is because of the exponent that goes with it. I think I said beta particle was somewhere around negative 26, 10 to the power of negative 26, and this one is 10 to the negative 31. So the negative 31 makes it smaller, much, much smaller than the alpha particle. Alright, so on to our next term, which is the fourth term, photon. Photon is the fundamental particle of all waves in the universe. So microwaves, infrared waves, radio, light, gamma, infrared, every wave out there is made of photons. Photons, here's a bit of quantum physics for you. Photon is the quantum of light. Quantum means basically it's basic particle. So light is made of photons, so photon is the light's quantum. This is usually shot out of radioactive nuclei as gamma rays, very high energy photons. These can also be listed as gamma particles, so there's alpha, beta, and gamma particles. But mostly people like to call them gamma rays because it's much simpler. So a photon, a high energy photon, is a gamma particle. This is the fastest thing in the universe because this has no mass and is the speed of light, which is the fastest thing. Fun fact, this actually uses another thing in quantum physics called wave-particle duality. Wave-particle duality means this can act as a wave and a particle at the same time. I think, I'm not an expert at wave-particle duality. Quantum physics is a weird thing. So basically this can be a wave and a particle at the same time. One, because a photon is a particle. And two, photons make waves, I think. I'm not sure. This is also, I think a photon is also on the standard model. Here's a picture of the standard model right here. I think it's on it. Oh well. I think it's in the category where on my standard model that's over there, I think it's in a group called force carrying exchange particles. So that's basically the same group that another one, the carrier of weak force, is in. So we'll get to weak force in a while. Alright, so our fifth term is really some quantum weirdness for you. It's called Schrodinger's cat. I don't know if you heard about this, but this is a thought experiment. This is a hypothetical experiment that you're not supposed to do in real life because that would be animal abuse. The thing about the experiment, the context of the experiment, so there's a cat in a box with some poisonous gas and some radioactive material. If the radioactive material decays enough, it'll swing a hammer that'll crack the bottle, which is, I think, is full of cyanide gas, that will release the gas everywhere. Supposedly could be killing the cat in the box. But the thing about the experiment, you don't know if the cat is dead or alive until you open the box. So you can't be just like, oh, the cat is dead, but you can't be positively sure that the cat is dead before you look into the box. It's quantum weirdness for you. So, like I said, this explains the mysteries of the quantum world, which I know almost nothing about. So the results of this experiment, well, the thought results, not the physical results, don't do this. The results show that there could be two different realities at the same time. So the results of the experiment is that the cat is dead nor alive. So it's neither both, or dead and alive at the same time. I'm not sure. So, fun fact, this is thought in 1935 by Erwin Schrödinger, which is the person that put this. Alright, so we are on to our final term, our sixth term, weak force. This is one of the fundamental forces in the universe. So far, in this season, we talked about three. We've talked about gravity, strong force, and weak force. There are four fundamental forces. We will get to the last one next week. So this is the force of attraction between quarks, neutrinos, and electrons. This creates fusion and fission. So basically, this is kind of like an extension of strong force, but for little tiny particles. But this, despite its name, it's not the weakest fundamental force. This is 1 billion trillion times stronger than gravity. So you could say that gravity is the weakest force, and I'm guessing this is the second weakest force. The range of that weak force can work in, remember the range is how much the force can be applied to. It can be applied to 10 to the negative 18 meters. So this has to apply in very small spaces. Fun fact, the carrier, or the particle that carries it throughout the universe, is the W positive, W negative, and Z0 particles. These are also known as the weak bosons, which are in the same family group as the photon, which is, like we heard, is the quantum fundamental particle of light. So these, like I said, are force-carrying exchange particles. So I think we covered all our key terms for today, so let's get to the announcements. I don't have an experiment for today. Well, editing is a struggle sometimes, so the outro film was corrupted, so we're gonna do the outro here. Alright, so announcements. Next week is the final episode of Season 2 of Prietology. We are done with the second season. So, Season 2 ends, we're done with physics episodes after next week, and the topic will be electricity and magnetism. We're going to end the season with electricity. So, we're going to talk about the final fundamental force, which we haven't talked about, which is electromagnetism. And then we'll get into electronics, current, inductors. I don't think we're going to get that deep, but conductors, insulators, current, voltage, generators, electromagnetism. So yeah, that should be fun to do. Also, second announcement, Cuphead will start next week, so stay tuned for that. Well, thank you for watching, and if you like this video, leave a like, and consider subscribing. See ya. Hi everyone, welcome back to Dprieto TV, and welcome to the end of Season 2 of Prietology. We're finally here at the end. Apologies for uploading this video super late, because, well, but finally we are here for Season 2 finale. Episode 6, Electricity and Magnetism. So, let's start reviewing the key terms. Alright, so let's review our key terms. So we have electricity, static electricity, electric current, magnetism, electromagnetism, generators, and semiconductors. So let's just get right on and start with the first term. So, electricity. This is basically one of the basic things that we'll be talking about today. So, electricity is made when electrons flow through a conductor. So, it could be metals, it could be some conductive wool, I think, iron wool. Basically metals. So, yeah, if it's metallic, it can conduct electricity. So basically it's when they flow through conductors. So the electrons move because of something called EMF, or electromotive force, which is known as voltage. Voltage, represented with a capital V, is voltage, named after Alessandro Giuseppe Volta, I think. So electrons, whenever they flow, they try to go near positively charged protons so they can connect the link, and that's when a circuit is formed. The word electricity comes from the word electron, which is Greek for amber, and you can guess that's where the word electron comes from. So when electrons flow through a wire, current is created. So you can basically, like a stream of electrons flowing through a wire, and streams of water are also sometimes called currents. So that's what I'm guessing the word current comes from. So a fun fact, the annual global electricity around the world, the amount of electricity produced is 8 to 82,000 trillion joules. That is a lot. Alright, so our second term is static electricity. We know what static electricity is. It's when you touch, like, you rub your feet on the carpet. There's not a carpet on the floor. And then you touch something metallic, you feel a zap. That is static electricity at form. So it's an electrical charge that remains in one location. Like, your body gets charged, and then you discharge on a conductor. So this can cause lightning, which is a weather phenomena when the air gets ionized. This is caused when two insulators, so let's say these two books, rub against each other. Some static electricity can be made, but not much because of what they're made of. So the process is that two insulators touch each other, electrons are taken off each other, leaving one with an opposite charge. So basically one likes to take electrons, one gives the electrons. So it's an exchange. So some fun fact, a normal lightning voltage, as we were talking about, the normal voltage of a lightning bolt, 100 million volts. Basically it'll fry you to a crisp. Alright, term number 3, electrical current. We're still in the electricity stuff. So electrical current is a form of energy by moving electrical charges along. Like we talked about when we said electricity, basically kind of like a flowing river of electrons and charges. And if you didn't know, electrical charge is measured in something called coulombs. C-O-U-L-O-M-B-S, if I'm not wrong. That's measured with a lowercase q, so something like this, I think. It looks like a little a. So this can be measured in amps or amperes, which is a capital A. And this can also be turned into light, motion, sound. So basically this is kind of like the basis for electricity, but it can transform into anything. It also can be formed with chemical potential energy, which can help give kickstart to current. Like a battery, these batteries, one here, this uses chemical potential energy, like we talked about a while ago. So the potential energy is stored, and then when you connect, I have some wires here, when you connect two insulators, electrical current starts flowing through the wire, thus produces electrical current. So a fun fact, the speed of electrons in a wire, I think with no resistance, is 1.01 millimeters per second, which is somewhat good time. Alright, term number 4 of 7, magnetism. We are done with electricity now. Now we're going to get into some magnetism. Magnetism is an invisible force made by certain substances, only ferromagnetic substances, which are substances that can create magnets. So iron, cobalt, and nickel, I think, are the only ones. This is measured in Teslas, no, not the car, named after a brilliant physicist? Was he a physicist? I don't know. Scientist Nikola Tesla, which is measured with a capital T. He helped create the electricity system that we know today. So it has the magnet. I don't have a magnet on me, but they both have north and south poles, which attract, and then opposites attract, like charges repel. Same with magnetism. So magnetism's power, the word magnetism comes from the spin of electrons. Here's a model atom. It comes from the spin of electrons. So I'm just going to try to spin it like that. It comes from that, and that's how magnetism is made. And certain elements have that unique spin that makes them magnetic. The magnetism can actually be found in hard drives, so like those floppy hard drives and MRIs, which are used to scan the brain and the body, and security tags for security purposes. Fun fact about magnetism, the magnetic poles of the Earth, they shift every year by 40 kilometers, which is the same as 25 miles, so that's a pretty big shift on a global scale. Actually, now that I realize it's not that big of a shift, considering how large the world is. Alright, term number 5. This is the last of the 4 fundamental forces that we've been talking about in this series. So we've talked about gravity in, I think, episode 1, strong force in episode 4, and weak force last episode in episode 5 when we talked about radioactivity. This is the final one, electromagnetism. As I said, it's one of the fundamental forces of the universe. It's the force of attraction, like gravity is the force of attraction, but this is the force of attraction between charged objects. This can be carried by waves and radiation. I think not last time, but in episode 3, we talked about the electromagnetic spectrum. That's where electromagnetism comes from. It makes all waves and all light, so it's pretty important to us. This is one of the only forces that you actually feel. This is actually the only force that you can feel on your body. When you're like shocked, when you get like zapped by static electricity, that you're feeling a fundamental force. It's the only one you can feel in the universe. This also lives on opposites attract, which is basically how all of our key terms live. And the range of this is infinite, unlike weak force and strong force that can only work in the tiny spaces of the atom. This works infinitely. So the fun fact about this, the carrier, or the particle that carries it throughout the universe, is called a photon. We learned about a photon last class, I think? Yes. It makes all light, all waves, so its carrier is photon. Alright, second to last term, generators. Generators are the things that power our life. They use electromagnetism, which we just talked about, to make electricity. They power everything in our universe. Not universe, but in our world. So how they're made, if you spin, I don't have a magnet, but let's pretend this battery is a magnet. If you spin it around a coil of wires, so let's just say this is a coil of wire. Let me just put it together. I think I can just snap it on. There we go. So I'm going to hold the wire, I'm going to make it a little smaller. I hold the wire like this, I don't know if you can see it, and then I spin a magnet. I don't know if it's in this direction, but if I spin a magnet with the poles, because magnets have the poles, so let's say this is north, this is south, the poles go that way from north to south, so it's like a circle. And for the electricity to be created, the poles have to interfere with the wire to help create the voltage. So if you spin it this way, I think, you'll create some electron. So basically, if you spin a coil of wire inside a magnetic field, or the other way around, and the electrons move, you create current, which means you create electricity. Power plants use this, but they make large coils of wire, and then they spin giant magnets in them to create electricity, and that's the thing that powers our stuff. So a fun fact, the output of the largest power plant in the world, which I'm not sure where it is 8.2 gigawatts of power. Basically, 8.2 billion watts of power. That is a lot. Here we are, everyone. Term number 7. The final term of this lesson and the final term of Prietology Season 2. Semiconductors. Semiconductors are mysterious materials that don't really like to conduct electricity, so they semiconduct. That's why they're called semiconductors. These are actually widely used in computers, so all those like high-tech gaming PCs that you guys have, those use a lot of semiconductors. These are made from elements. I think we talked about the periodic table in the first ever Prietology lesson. Go take a look right here. It's made from elements called metalloids, or as I call them sometimes, the semiconductors. So silicon and germanium, mostly made from silicon, is what most of the semiconductors are made of. They can somewhat conduct electricity. That's why they're called metalloids, and because they somewhat conduct. Doping, a process called doping, helps electric current pass through semiconductors, so basically kind of adding a little bit of conductivity. The final fun fact of this season, the industry value of semiconductors is $200 billion a year. Basically the entire global market today in our modern world strives on semiconductors. All the technologies, they like to use semiconductors. I have to do this one last time. Well, that is wrapped up for season 2 of Prietology. So let's move on to the final experiment of the day, which we actually had this lesson. So let's get started. Alright everyone, this is experiment of the day. It's called electromagnetic field. What you need is a metal bolt or a screw, so something like this. Some paper clips, so any paper clips can do. Some insulated copper wire, I have mine here. Preferably, it would be better if it was 12 inches or 30 centimeters. A battery, some electrical tape. Make sure you have some electrical tape. Regular tape doesn't really work with this. And scissors. Alright, so the procedure, so first you have to wind our wire around the bolts. So I'm going to start winding this. Alright, so now, oh come on, it just unwinded on me. Wow. And then you want to leave about 2-ish inches to spare. This is about 2 inches, I think. So now we're going to tape the wires to the ends of the batteries with electrical tape. I'm going to hold my wire also together with electrical tape, so this may take a while because this electrical tape's a little non-sticky. Alright, I think I have my bolt. It's a little tacky, but we'll make do with what we have. Now to tape my battery, I gotta get some more electrical tape. Oh, I think this may actually be a little too much. Let's just get the tape off. There we go. Now to tape it to the battery. Come on, work with me, batteries. Because I'm basically holding the electromagnet together. I don't know if this will really work. Ah, come on, I just let it go. Alright. I gotta put it back. Alright. Come on. Ooh! The battery. Oh goodness, the battery's actually hot. Surprising. I think that means we have current running through our wires, which we want current to run through our wires. Ooh, it's getting a little toasty. But let's see if we can pick up some some paper clips. Ah, come on. Alright, yeah, we're gonna really need that electrical tape. Alright, brief intermission. There is current going through these wires. Yeah, these wires are actually heating up. I don't think my electrical tape is good enough. Anyway, but let's just hold it like this. There we go. And let's see if we can pick up some of our paper clips. Oh, it just did it. Watch. Oh, come on, why is it not doing it? Come on, paper clips. Okay, I'm gonna take the electrical tape off. And then now I'm gonna try being it up with the screw. Come on, screw. Ah, come on, it's not working. This battery's getting really hot. Probably shouldn't continue doing this. But what's supposed to happen is that the bolt is supposed to be able to pick it up. Well, for the last experiment of this season, it kind of failed. So, let me tell you what has been happening. So what's supposed to happen, actually, the electrons make the magnetic field as they run through the wire, and then they wrap around this screw, and a wire coiled around the core makes a bigger magnetic field. So this was our core, and the wire wrapping it around helps create the magnetic field. In this case, the core is our bolts. We call this an electromagnet because it's the only it's only magnetic when electricity flows through it. That's why it's called an electromagnet rather than a magnet. So you could turn it on and off by disconnecting it. Well, I would be able to turn it off. Well, that concludes the final lesson. Let's move on to announcements. Oh, announcement time. Well, everyone, another Prietology season done. Good job. Good job. Thank you guys for watching this. Thank you for being on top of this. This is a big thing that I've been able to do a second season, guys, with your support. So, we're going to be done with physical science for a while. So, we talked about in this season, just a recap of the little season. First, we talked about motion and gravity and force and mass. Then after that, we talked about potential and kinetic energy. Then we talked about waves and electromagnetism, a little bit of electromagnetism, some amplitude, frequency. Then the fourth episode, we talked about atomic structure, getting even deeper into atoms and see what the atoms, protons, and neutrons, and particles are made of. And then we talked about radioactivity last lesson. And then in this one, we covered electricity and magnetism. Whew, what a tiring lesson this was, and also this season. Alright, so like I said, physical science, so chemistry, physics, we're going to be done with that in a while. The topic for season 3 of Prietology is biology. We're gonna get into some life science. So we're gonna talk about DNA, skin, cells, plants, animals, how life is created. Well, we're not gonna get a little too deep in that. But we're gonna talk about like how cells mutate and how they create it. It's gonna be fun. We will start this next season, season 3 of Prietology, in late March. So don't expect another Prietology lesson until March. Late March. So maybe 22nd of March is probably when we're gonna do it. So maybe late 20s of March. So yeah. And so also, if you just for you know, so you guys know, I'm gonna be a full steam on videos. I just took a little break myself because, well, creators need breaks because they put a lot of work. So after this, full steam ahead. We're gonna go full steam ahead with Prietology. Next week is a gaming video as always. So that should be fun. Well, thank you for being with me for another episode and for another amazing season of Prietology. We are done with physics and we are done with chemistry. 2 seasons already. Well, this is where I say goodbye and thank you for watching. See ya.